So last time we looked at 6.3, which is graphs of sine and cosine. Today we're going to look at graphs of the 4 other trig functions. Okay, we'll spend a little bit of time with the transformations, not a lot, because we've already done them so much, and they're exactly the same as they've always been. Stretches, compressing, all that stuff. Okay, so let's start out by graphing tangent. Okay, what we're going to do is try to rewrite tangent using a trig identity that we have. And we're going to write it as a fraction. Okay, and I'd like to write tangent using 2 other trig functions that are more basic that we already know a little bit about. Anybody remember how you can write tangent as a fraction of 2 other trig functions? Silvio?
Sine over cosine.
Yeah, you can write it as sine over cosine. Now we know hopefully quite a bit about sine and cosine, especially where it hits 1, 0, -1, things like that. So first thing I want to figure out is where does this graph cross the x-axis? All right, well, it's going to cross the x-axis whenever it hits 0, whenever the y value hits 0. So how could tangent be 0? Think about looking at that fraction on the right-hand side. Basically, you're asking yourself when that fraction could be 0. So how can a fraction equal 0, just in general?
When the numerator equals 0?
When the numerator equals 0. So in this case, that's sine. So if you can find a value that makes sine come out to 0, you're going to make tangent come out to 0. So let's write that down. Does anybody remember what value for x would you plug in for sine and you'd get 0? Think about the graph of sine. Yeah?
0?
Yeah. So when x is 0, where else? Sine hits 0 again at another point in that period. 0. Did you give me degrees or radians? Because it's actually the same. Which one did you pick?
Radians.
Okay, so you did 0 radians. So let's also do the next answer in radians. What's my other answer where it hits 0? Yep. Pi. Good. So now we know 0, pi, and remember this is periodic, so there's an infinite number of zeros. Sine just keeps crossing the x-axis infinitely many times. We're just going to write down a couple. That'll help us to sketch one small section of tangent, and then if we need to sketch more, we can just copy what we've already done. Now, looking at that fraction, okay, if you divide by 0, that's when you get a vertical asymptote. Right? So there's a vertical asymptote whenever cosine x equals 0. Because there's a vertical asymptote, that means this graph is not, or this picture would not be what if you tried to draw it? Yeah.
Continuous.
It's not continuous. Tangent is not a continuous graph. It will be periodic because it's based on 2 other periodic functions, but it won't be continuous. Okay, and then what we'll do is we'll check a value on each side of an asymptote, okay, just like we've done before. So for this one, anybody give me a value that would make, this time just give me one, that would make cosine 0. Where does cosine hit 0?
2 pi?
That's where sine would hit 0, at 2 pi or 360. Cosine actually wouldn't hit it there. It happens pretty early in cosine. Because remember, cosine starts at the top, and then the first place it goes is down.
Pi divided by 2.
Pi over 2, yeah, 90 degrees. If you plug in pi over 2 into cosine, you get 0. Try it. And if you get 0 in a fraction, it's in the bottom, you just divide it by 0. That's a vertical asymptote. Okay, so let's see if we can do that. Okay. First thing I'll do is I'll sketch my vertical asymptote. Okay, so let's put that in. In fact, you know what might be helpful if we sketch another vertical asymptote, just so we have a kind of an area that's a little bit more bounded to look at. The next place cosine hits 0 is at pi. It goes down to -1 at 3 pi over 2. Okay, so let's draw an asymptote in there as well. And it turns out you're going to get another vertical asymptote on my graph every other mark. So you're going to get one at 5 pi over 2. Okay, going the other way, you get one at -pi over 2, -3 pi over 2, and so on. Okay. Any question on that? All right, so now let's go back to what we looked at. Let's graph the x-intercept. Okay, so we know that tangent is going to cross the x-axis. We've got a couple spots, at 0 and at pi. So it's going to cross it here. It's going to cross it here. It's going to keep crossing it basically right in the middle of the asymptotes. Okay? I'm not going to sketch every one of these periods. I'm going to focus on the one that's between the two green lines. Okay? And if you wanted, you could just copy and paste that over and over. All right, next thing I'm going to do is I'm going to go into my table, and I'm going to look at values that are very close to pi over 2 and 3 pi over 2. I think I'll do it as a degree because that's easier to type in. It's easier for me to type in like 90.1 rather than type in like pi over 2 plus 0.1. Okay, so I'll do it as a degree. You know what? In fact, I don't even need that calculator. Let's just use this one. Okay, let's pick a value that's just after 90. Okay, like 90.01. So take 90.01, take the tangent, and we get a value that's very low. Okay, -infinity. Now let's try a value just before 3 pi over 2. So that's 270. Let's try like 269.9. Take the tangent. We're heading up towards positive infinity. So even though this isn't a continuous function, between those green lines it is. Okay, so it's going to kind of come up, curve, and go up like that. And that's basically your graph of tangent. If you repeat that over and over, you could draw multiple periods. Okay, let's look at it. Let's look at it on here. Tangent, and let's do zoom 7. Okay, what's happening on the left-hand side is half of a period is being cut off. In general, when we do sketches, we'll try not to cut periods in half. So for example, if I asked you to sketch 3 periods of this function, I'd rather you not sketch a half, a whole, and a half. Even though 2 wholes and 2 halves make 3, I'd rather you just sketch 3 whole periods rather than breaking things in half. Okay? So on the screen here, you're seeing you're seeing 6 periods of tangent. 5 whole ones and then 2 halves. And we sketched that one right there. Right. Any question on that? So that's your graph of tangent. Okay, very simple to see where it comes from based on using sine and cosine. Well, for cotangent, we can go through all the same things again. All right, so we won't go through it in as much detail, but with cotangent, what happens is the fraction flips. So now your x-intercepts here are where cosine is 0, and your vertical asymptotes are where sine is 0. Very, very similar to what we did before. And then we could go through and investigate a point very close on each side of the asymptote. But it turns out if you do all that, that's what you're going to get. So you get vertical asymptotes at 0, pi, 2 pi, 3 pi, so on. You're going to get an x-intercept at pi over 2. Why? Because the cosine of pi over 2 is 0, and that makes the fraction 0. And then if you check a point on each side of the asymptote, it's kind of reversed. If you look at the curve, it's curving down as you go to the right, rather than up. Okay, you can see the difference. So the asymptotes are shifted by 90 degrees, and the curve goes the other way. That's the graph of y equals cotangent. Hey, any questions on that one? Okay, and here you're looking at one period. If you had to type that into your calculator, there's two ways you can do it. You can type it in as cosine divided by sine, or there's another way you could type it in. Does anyone remember the other way? Almost what I have there. I could reuse some of that. Yeah, for cotangent. What's another way to type in cotangent? Yeah, 1 over tangent. Okay, and you get the same, pretty much the same picture. All right, so we know that this should be, yeah, that's good. That's correct. Any questions on that one? Again, you're looking at 5 periods, 4 complete ones, and then kind of a half and a half again on the ends. Okay, so that's cotangent. So looking at our picture, I think we can see like how often these asymptotes repeat. If you get one at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, how often are they repeating? In other words, what are we adding to get from pi to 2 pi, to get from 2 pi to 3 pi, 3 pi to 4 pi?
Pi?
We're adding pi, right? And it works exactly the same with tangent. Look at it's easier if you don't want to look at the fractions, look at the x-intercepts. 0, pi, 2 pi, 3 pi. Things keep repeating here every pi units. So the period of tangent and cotangent is pi. For sine and cosine, it was 2 pi. This one's pi. Right, so this is the periodic property for tangent. If you take the tangent of an angle, or you take the tangent of that angle plus any integer multiple of pi, it comes out the same. Right, so let me try to, let me do it in degrees. I'll take the tangent of 10 degrees. Okay, so tangent of 10, and let me switch over to degrees. Sure. Okay, so it comes out to 0.176. Now if I take the tangent of 10 degrees, and I'm going to add a multiple of 180. In fact, I'll just add 180 times 1. Comes out the same. If I take the tangent of 10 degrees and add, let's do 7 times 180. Okay, that's still an integer multiple of 180. It comes out the same. So if you take the tangent of an angle, or any angle plus an integer multiple of 180, you're always going to get the same answer. Okay, we could even do, let's see, negative. You're still going to get the same thing. Okay, and that also works for cotangent. So if you take the cotangent of an angle, or that angle plus or minus any integer multiples of pi, you always get the same thing. So that just says n is an integer. Okay, and if it's kind of confusing algebraically and you still looked at my example and you're not sure there, you can also think about it as a picture. So let me put my graph back up of tangent. Or cotangent, I guess it didn't matter. Okay, so here's my graph of tangent. Take that. And imagine putting in a horizontal line. Okay, it doesn't matter, anywhere. Okay, and I asked you what that value was right there. Okay, looking at it, maybe it's about point, if those marks go by ones, could be like 0.7 or something like that. Well, to get to the next spot over, basically you just did plus pi. What's the difference between the height in those two dots? Yeah.
0.
0. There's no difference. They're the same. Right? And then if you go to the next dot over, if you add another pi, so now you just added 2 pi. Right? Well, we're in degrees, so it would be 180. But the point is, if you keep adding or subtracting pi to a point, it brings you to another point at exactly the same height as the previous point. It's the same y value. Okay? And that happens with cotangent as well. So any question on that? We saw the same thing with sine and cosine, except it was every 360, or every 2 pi, not every pi. All right, so this is an idea we've looked at 5 or 6 times by now. So we saw how we can transform sine and cosine. Well, for tangent and cotangent, the transformations work exactly the same. There is no difference. So if you add or subtract the number inside parentheses, that's your phase shift. If you multiply x by a number, that's your period change. If you multiply by a number in front of the trig function, that's a vertical stretch or compression. Depends if it's bigger than 1, c would stretch. If it's between 0 and 1, it would compress. And then we also talked about having a negative here. Okay, if c is negative, that's going to cause a reflection over the x-axis. And then d is your vertical shift. So if d is positive, you shift up. If d is negative, you shift down. Remember, with phase shift, it's the opposite. A and B do the opposite of what you would expect. Plus is going to shift left, and then minus is going to shift right. Big numbers for B make the graph more compressed. Smaller numbers, like 1/2, 1/3, 1/5, smaller numbers, stretch it. And I put A, B, C, D because that's the order you would do the transformations in. Do your phase shift, period change, then amplitude, and then vertical shift. Hey, any questions on that? Right. So again, if you basically just take the equation you had before, change sine to tangent, it's the same formula you had for that. All right. Since the period is different, our formula to find the period is different. With sine and cosine, we used 2 pi divided by b. Well, now we're using pi divided by b, where b is the number that's in front of x. All right, so we know, by using that formula, we know what the period is, but what we have to figure out now is where would our asymptotes be? If we stretch or compress or we do something, well, All that's really going to affect where the asymptotes are two things, A and B. C does not affect asymptotes at all. Asymptotes run vertical. So if you have an asymptote running vertical, stretching an asymptote doesn't do anything to it horizontally, and shifting a vertical asymptote up or down, that doesn't do anything to it. Okay. Did you move it left and right? That'll affect it. Or did you stretch or compress it? That'll affect how often your asymptotes occur, okay, either more or less frequently. So the idea is, can we just find one asymptote? If we can find one, and we have this formula to find the period, then we can find another asymptote by starting at the one we found and then adding the period to it, and then adding the period again and again and again. Okay, so how do you find one asymptote? Well, you know that tangent is undefined when x is 90 degrees, or pi over 2. So we're going to start with that fact. So you're going to take your argument, which is this part. It's the argument to the tangent function. It's what's getting plugged into it. And you're going to set that argument equal to 90. If you can find a value for x that forces that argument to be 90, you just found a value for x that makes an asymptote. Then once you have one asymptote, that's your starting point. Use your formula, find your period, and then you can add or subtract that period as many times as you want to find more asymptotes. All right, so what we'll do is we'll look at a couple graphs. We're not going to spend an hour doing every single transformation, shifting, stretching, like we did with sine and cosine. But we'll take a look at some. In fact, some I might just give you a graph. I'll take 2 pictures of what was on a calculator screen, and I'll ask you question about the pictures. So I won't even make you graph some of them. Okay, so this example says to find the period of tangent 2x. And you don't have to sketch anything by hand. Find a complete graph, and I'd like you to show 3 complete periods. By complete, I mean, please don't show me like a half, and then 2 holes. Okay, let's make 3 nice connected periods on the screen. So that means we might need to adjust our window a little bit. Okay, start with the period. Okay, what's our formula to find the period? Here's the ball, Michael.
Pi over b.
Yeah, pi over b. In my problem, tangent 2x, what's b?
2x.
Nope, that's not b, just the b. And what's b?
2.
2. Okay, b, if you look back at that formula, b is the number that's in front of the x, okay, not the x itself. Good. So now we know our period. So once we find one asymptote, all we have to do is add or subtract pi over 2 from that as many times as we want, and we can get more asymptotes. So what's happening here? Did this graph compress, or did it stretch? Right? Yeah, it compressed. Before we had asymptotes every pi radians. Now you're getting them twice as often. You're getting them at every pi over 2 radians. Okay? So in terms of degrees, you have an asymptote every 90 now, not every 180. Okay, so let's find a complete graph that shows A complete graph that shows 3 connected periods. Right, so first thing is, let's type in our function. Now, how big of a window do I need? This is the length of 1 period, pi over 2. I want to show 3 periods. So how big should I set my window? Yeah?
So your third, basically, because if you think about it, you have pi over 2, then your next asymptote is going to be 3 pi over 2, and then your next one's going to be 5 pi over 2, so you want to set it greater than 5 pi over 2.
So now asymptotes are occurring every pi over 2, not every pi. So if you added pi to this, the next one would be 3 pi over 2.
It would be pi. Your next asymptote would end up being pi.
Pi, yep.
So then if you want 3, it would end up being 3 pi over 2, so you probably want to set it at about 2 pi.
Yeah. Well, you know what? Let's try to show exactly 3 periods. So if we set it at 2 pi, that's actually going to give us a little bit more of a 4th period. So let's try setting it from 0 to 3 pi over 2. Right? Pi over 2 is 1 period. Triple it, you get 3. The only problem is you're going to have the right width, but I don't know if it's going to be in the right spot. Okay? If it's in the wrong spot, you're going to cut something in half. Okay? So first of all, let's do this in radians. And let's set our window from, you can start with zoom 7 if you want. And we can see that's clearly way too many periods. Okay, so let's try from 0 to 3 pi over 2. Oh. That is 3 periods, but it's not the way I would like it. You got 2 holes, and then you cut one of them in half and in half. So what could I do to fix that? I got to change my x min and x max. And relative to each other, I don't want to change the size of the window. I just want to slide the window a little bit. So if you want to add something so that maybe it starts at that first asymptote and goes from there. But let's try something. Yeah?
Start from pi over 2 to 2 pi.
Okay. So we could start right at that first asymptote. Pi over 2. And now how did you get 2 pi?
I just shifted everything by pi over 2.
Yeah, he just added pi. You know what you could have done if you wanted? If you want to shift everything by pi over 2, you could just do plus pi over 2 and do the same thing. I think I messed it up, and then plus pi over 2. Okay. This one, I think we had 3 pi over 2, so it would shift to 2 pi. Well, we shifted it, but I think we shifted it too much. We shifted it so much that now we broke another period in half. So instead of shifting it by pi over 2, what could I maybe shift it by? Not quite as much of that, where we kind of went halfway too far.
Pi over 4.
Yeah, let's try shifting it by pi over 4. Okay, so sometimes this involves just a little trial and error till we get used to it. Okay. Well, let's see if I can. All right, so we started off at 0, and then we had 3 pi over 2. Okay, I'm going back to what we had originally. And now I'm going to add pi over 4 to each one of them. Why am I doing it this way? Because I don't want to have to find the common denominators and go through all that work. So let's try shifting by half the amount. Add pi over 4. And add pi over 4. Good. That's perfect. Now we've shown 3 complete periods, and they're not broken. Okay? So when I do it, again, I generally start out with x min at 0, and then find what x max would have to be. And sometimes I get lucky. Right away, that window works. If it doesn't, then I'll add or subtract something to both of those values so that I can find a complete window. Okay? And now if you wanted to write your decimal for x min and x max, that's fine. That's what I'd be grading on the test. Okay. So x min is 0.79 and x max is 5.50. Now if you wanted the exact answer, well, that one was pi over 4, and x max is 3 pi over 2 plus pi over 4. So you have to find a common denominator and add them up. Okay, but I just want you to try to understand how to find the window on the calculator. Okay. Questions on that? It's a little tricky, not too bad. Okay, this time I have two graphs already sketched, and I want to know which one is the graph of 2 tangent x and which one is the graph of 5 tangent x. So here you've got to know what the 2 and the 5 are doing to the graph, and imagine if you did whatever it's saying to do. Yep.
I think the 510x is the one on the right
Okay, how come?
because bigger numbers like compress it.
Well, for horizontal stretches, they do, but not for vertical. Anything that's outside these parentheses pretty much does exactly what you would expect. So the C and the D kind of use common sense. It's the A and the B that are reversed. Yeah?
The one on the left would be 5 tangent x because it stretches it out, so it'll be a lot closer to a straight line than a very curving line.
Yeah. The more you stretch it, the more that curve kind of starts to disappear, and it's never straight, but it looks a little straighter. Okay, so 5 tangent x is on the left, and 2 tangent x is on the right. Yeah, but that's an easy thing to mix up if it's stretching or compressing. All right, so just try to make sure you remember the difference between the vertical and the horizontal. Okay, any question on that one? All right, so let's look at secant and cosecant. So we're going to use the same kind of reasoning we did before. First, I want to rewrite secant as a trig function that I'm a little more familiar with. It's the reciprocal of cosine. So is secant going to have vertical asymptotes? What do we think? Is that possible?
Yes.
Absolutely. If it's possible to make the denominator 0, then you do have vertical asymptotes. We've already talked about cosine can definitely be 0. In fact, the first place it hits 0 is pi over 2. So whenever cosine is 0, we're going to have a vertical asymptote. When cosine equals 1, so does secant. Why? Well, if you change the denominator to 1, find a value for x, such as 0. When x is 0, plug it into cosine. Cosine of 0 is 1. 1 divided by 1, 1. So when cosine of x equals 1, so does the secant. When cosine of x equals negative 1, so does the secant. It also equals negative 1. Okay, think of 180 with cosine. You plug that in, you get negative 1. 1 divided by negative 1 is negative 1. All right, so that gives us at least a couple different points we can graph. My next question is, does secant ever equal 0? Look at that fraction on the right-hand side. 1 divided by a number. Can 1 divided by a number ever be 0? No, that's not possible. I don't care. Even if you we're pretty limited with cosine. Cosine only goes as high as 1 and as low as negative 1. But pretend you could let this number in the denominator be anything you wanted. That fraction still would never be 0. Even if you did 1 divided by a million. It's pretty small, but it's not 0. So secant can never hit 0, which means it never crosses the x-axis. There are no x-intercepts for secant. Every graph we've done so far had x-intercepts. Sine, cosine, tangent, and cotangent. This one won't. Okay, so let's see if we can sketch a few asymptotes and get a picture. Everybody have those facts? Okay, so this one is going to be periodic. It's going to have a pattern. So I've already sketched in some asymptotes. Okay, how did I get them? Think of values that make cosine 0. 90, pi over 2. That makes cosine 0. 270, or 3 pi over 2. That makes cosine 0. Once I have two asymptotes, now I know the distance between them. I can just keep making as many asymptotes as I want. Just keep that distance consistent. Okay, so we are going to check some points to the left and the right of these asymptotes. But let's use this fact. Okay, when does the secant equal 1? Well, ask yourself, when does the cosine equal 1? Okay, so I'm picturing graph a cosine in my head. Starts at the top. When does it equal 1? Well, when x is 0. When x is 0, cosine is at its highest. Okay, that's a point. Okay, when does that graph equal -1? Well, ask yourself, when does cosine equal -1? Okay, so cosine equals -1 right here. That's its lowest point. That occurs at pi. Okay, so when you plug in pi for x, cosine becomes -1, and so does secant. That's as close to the x-axis as this graph is ever going to get. It can't hit any values in between here. Because the values in between 1 and -1, those are all decimals. Like 0.5, 0.7, -0.8. That's not possible. To get decimals like that, you have to divide by a bigger number in the bottom than you have in the top. Well, I can tell you right now, cosine is never going to get bigger than 1. So you'll never have a bigger number in the denominator than you do in the numerator. It's not possible. So you'll never get a number like 0.5, like if cosine hit 2. It doesn't hit 2. It only hits 1. Okay? So there's going to be kind of this gap in the middle where nothing gets hit. Right, now let's check the behavior of the asymptotes. Let me use my table because that's a little faster. I don't need to. I could use the scientific calculator again, but I just want to do it a little faster. So the way we got to type it in, it's 1 over cosine. Okay, the only reason I'm picking degrees is because I think the numbers are a little cleaner to type in. So I'll translate these radian measures to degrees in my head. If you want to use degrees, that's fine too. Okay, -90. Okay, a number just before that, -89.9. Way up, okay, approaching infinity. So you might think, oh, wait a minute, is this going to look like tangent and curve down? Nope, can't ever cross the x-axis. So something has to happen after this point. It can't keep going down, and it's not connected to the next one either, because we have these asymptotes. Right, so let's try a number just before 90. Let's try 89.9. Positive infinity again. What does this shape kind of remind you of if I start to connect those dots using a smooth curve? Okay, everything here is nice and smooth.
Parabola.
Yeah, it looks kind of like a parabola. And it has that U shape. Let's check the other section. Check 90.1. Okay, you get negative infinity, and trust me, when you check the next one, you'll get negative infinity there as well. So with this one, you get these kind of alternating U shapes and N shapes. This is one period, not two. Okay. The next one would be I need 2 more asymptotes. Here's a second period right here. Now you're looking at 2. Okay, once you get 1, it's very easy to sketch as many as you want. Okay, let's look at the graph of this on our calculator. Okay, so the section that we drew are these two complete ones. On the edges here, we've got 2 periods. This U shape at the top is a half. That's a quarter, and that's a quarter. So you get a quarter and a quarter makes a half. Another half, that's a whole, and then a whole and a whole. So there are 3 periods on the screen, but they're really kind of broken up. Okay. We'd have to just shift our window a little bit if we wanted to fix that. Okay, but there's secant. So to find the period of secant or cosecant, our formula goes back to 2 pi over b. We've seen that one before when we did sine and cosine. Okay, why is it 2 pi? Well, pick 2 points on the graph that are common and look at the distance between them. Pick this one, pick that one. That's a reoccurring point. How far apart is it? This one's at 0, that one's at 2 pi. So points on this graph reoccur every 2 pi. That's pi. That would be 3 pi. So this is the same idea as with tangent. If you have to sketch this one and you're not sure where to start with your asymptotes. Find 1. Okay? How do you find 1? Well, with secant, you know it's undefined at 90 degrees. So if you can find a value for x that causes your argument to be 90, you just found a vertical asymptote. Then once you have 1, you can use the length of your period and sketch as many asymptotes as you want, just like I did up above. So for example 3, I don't want to sketch anything. I just want to write down the domain, the range, period, and the vertical asymptotes. Start with the domain. How would you describe the domain here? It's not, you can't say all real numbers because there's an infinite amount of numbers that don't work. Every asymptote doesn't work. So you could start off by saying the domain is all reals, and then it's easier to exclude the ones that don't work. Except, and now this is the tricky part. How would you explain the domain here is all reals except which numbers? Because you can't list every vertical asymptote. Pi over 2, 3 pi over 2. Somehow you have to describe it more generally. And you can't write all reals except the vertical asymptotes. Because I'm going to ask you what the vertical asymptotes are in a minute. So we've got to figure out, we actually have to figure out this part of it right now. Yeah?
So it's all integers of pi.
All,
All multiples of pi.
can you give me a value to, I got to start, so like if you said 0 pi, 2 pi, and 3 pi, those values are okay. And those are multiples of pi.
It would be all multiples of...
Pi is correct,
Yeah.
but starting from where?
Starting from negative pi over 2.
Okay, you could start from negative pi over 2. You can start from any asymptote you want. Okay? So pick an asymptote, start there, and basically the way we'll say it is all reals except x, where x equals pi over 2. That's one value that doesn't work, or any integer multiple added to that. K is an integer. So it's every real number except this vertical asymptote plus every other vertical asymptote that comes after it. And the asymptotes keep reoccurring. I'm just looking at my picture. They keep reoccurring every pi units. Okay, so that's our domain. Okay, our range, that's a little easier to describe. Well, it does go down forever, and it goes up forever, but be careful, it doesn't hit everything in the middle. Okay, so our range is from negative infinity up to, and it does hit negative 1. And then it's going to skip everything from negative 1 until you finally get back to 1. So from 1, and it does hit it, to positive infinity. Okay, so that's our domain and range. Period. Well, we just kind of looked at that using this formula. Okay. Period is 2 pi. Look at how often those points reoccur. How far apart are they? Every 2 pi. Okay, so this one's a little tricky if you look at the asymptotes. You're like, well, wait a minute. You just said to get from one asymptote to another, you add pi. But you're telling me the period is 2 pi. Yes, there's multiple asymptotes per period in this graph. There's 2. Okay. You could kind of, it depends on how you think of it. Okay, but I like to think of this as a period. Okay, what I basically tried to circle there, I've got 2 asymptotes right in the middle of that period. This one is on the edge. So I would count that with the next period. Okay. Right, so my period is 2 pi with multiple asymptotes per period. Okay, and what else do they want? Vertical asymptotes. Well, we already figured that out. It's all x's such that x is of the form pi over 2. Just pick any asymptote you want to start with. Plus, you can add or subtract pi times an integer. You can add 1 pi, 2 pi, 12 pi, 77 pi. Every time you add pi to pi over 2, you're going to get another asymptote. Okay, so that's your graph of secant. Well, for cosecant, I'm not going to go through the whole thing again. I'll show you the picture of it. You basically get the U shapes and N shapes again, except they're shifted a little bit. Okay, so let me show you. I'll put that there. That's for secant. Let me show you cosecant. What trig function do I need in the denominator to do cosecant? Sine. Like, well, wait a minute, doesn't it look the same? Well, not quite. It's shifted a little bit. That does look the same. But that's not what that was. Okay. So you look at the y-axis. On the y-axis, it cuts one of those parabola-like shapes in half, and on this one, it doesn't. So it's similar. Okay, but if you're going to go through it, what's your domain? Well, it's all x's except, or all reals except x, where x is of the form pi k. This time, my asymptotes start at 0, and I get another one every integer multiple of pi. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. So it's all reals except x, where x is of the form pi k. My first asymptote starts at 0. What about my range? Well, range is the same. Exactly the same as what we had before. Period, same as what we had before. Vertical asymptotes, we already said that. So all x's such that x equals pi k. And that goes in the negative direction too. Remember, integers can be negative. Negative pi, negative 2 pi, negative 3 pi, and so on. Okay, so if you want to go through it, you've got the picture, you could look at it and just compare it to what we did earlier, and I guarantee you'll be able to find the asymptotes and everything else. Okay, so any question on the cosecant? And if you get really stuck, all the answers are on page 350 of this one. I think it's same example number in the book as what I have on the board. Yeah?
So what were the things that were different from secant and cosecant?
So period is the same, range is the same. It's just your vertical asymptotes in your domain. So your vertical asymptotes here are all integer multiples of pi. Pi k, where k is an integer. And your domain is all real numbers except the vertical asymptotes, or except all numbers of the form pi times k. Remember, k has to be an integer. K can't be 3.2. K can be 7, can be 10, 106. It's got to be an integer. All right, so this one, just a graphing one. There's not going to be anything to show, so I just want you to watch how I do it. They want me to graph that and show 2 periods. Okay, first thing I'll do is remember how I type it in. It's 1 over sine, but in this case I need a 3. Okay, I'm going to start with zoom 7. So those U and N shapes go on forever. The calculator just has trouble sketching it. So I want to see 2 periods. Okay. First thing I'm going to do is look up, well, what's my formula? My formula is 2 pi over b. B in this case is 3. That's 1 period. Okay. Well, if I want 2 periods, double it. So 2 periods is 4 pi over 3. Okay, so I'll start with a window of 0 to 4 pi over 3. I guarantee you it'll show me 2 periods, but it might cut off something somewhere. So let's go in radians. It's the same graph we just had. I'm just doing it in radians. It also shows the U and N shapes a little better. It shows them continuing, which that's nice. All right, 4 pi over 3. I think I got lucky. Lemon has 2 periods, perfect. So I know I had the right width, I just wasn't sure if I'd have to slide it. This time I don't. So 0 to 4 pi over 3. And there's more than one answer to that. You could show me these 2 periods. You could show me the previous 2. Okay, but I generally start with 0, and I show the first 2 complete positive periods. Usually. Okay, but that can vary. And that's it. Any question on example 5? So your x min and max, in case you need them, was 0 to 4 pi over 3. All right, so you've already got this in your notes, but in case you need it again, it just puts it all on one page. For sine, cosine, cosecant, and secant, here's your formula for period. 2 pi over b. For tangent and cotangent, it's pi over b. Okay, and the last part is using the graphing calculator to solve equations. Okay, we've done this before too. Basically, as long as you know how to find an intersect, this part's very simple. So what does it mean if I have a periodic equation and I find one solution to it? What else does that mean? I have a periodic equation and I find one solution. Yeah?
Well, then couldn't you just add an integer and it would give you multiple solutions?
Yeah. And how many would it give me if I wanted?
Infinite.
Infinite. Okay, so think back just to a basic sine or cosine graph. Say I asked you, where does the sine hit half? Well, graph's not perfectly straight, but let's see if I can fix that a little bit. So the idea is that if you find one place where that graph hits the line, it's going to keep hitting that multiple times all the way down the graph. And there's actually two answers here per period. There's one there, and one there. So all the dots that are in red, those are like the same answer, repeated over and over. And all the dots in black are the same answer. Okay, so the point is, if there's one solution, there's infinitely many. And exactly as Marina said, once you find one, okay, use your calculator, get one answer, and then add to that any multiple of the period. If you add a multiple of the period, that's how you write all the solutions in general. Remember, n is an integer. Okay, so we'll finish up with this one. Let's just do example 6. The biggest thing you got to be careful of is make sure you find all of the answers in one period. Don't assume there's just one. There could be more than one. Like I showed on the picture of sine. There were two. Okay, could there ever be more than two? Well, generally, I don't think so. Think of a horizontal line and all the trig functions we've studied. Could it ever hit that graph more than twice in a period? Definitely not for sine or cosine. Tangent, in fact, tangent, your horizontal line, no matter where you put it, it's only going to hit it once. So tangent, you won't have to worry about more than one. Same with cotangent, and same with secant and cosecant. You've got U shapes and N shapes, but no matter where you put a horizontal line, well, there could be no solution. But at most, it's only going to hit it twice. Could hit once if it was just tangent to that minimum or maximum. Okay, so let's see if we can get this one. Where is the cosecant equal to negative 1.6? So type in cosecant. Type in negative 1.6. And let's do zoom 7. Now remember, you're looking for all the answers in one period. Okay? So this, what I just circled, that would be considered a period. If you look beyond what I circled, you're just repeating answers that I can get in the circled part. Okay, so what we want to do is find that and find that. Okay, and write those two answers down. That's our starting point. So second calc intersect. So we got 0.68. And what's the other one? Second calc intersect about negative, oh, that should be negative 0.68. It's like negative 2.47. What's the period of cosecant? Yep, 2 pi. So you could take any one of these answers and add a multiple of 2 pi. So plus, sometimes you see 2 pi k or 2 pi n. Really could be any variable you want. Just make sure you say k is an integer. Okay. So you found 2 specific answers, and then you're telling me that those 2 answers will repeat every 2 pi units. The next one, tangent 2 pi 5, would be the same thing. Find one answer, and then tell me that it repeats every pi units, because the period of tangent is pi. Okay. So any question on that idea? Yeah.
How do you know that one period goes diagonally like that instead of the other one?
Well, I mean, you could break it off into, like I mean, you could look at it the other way if you wanted. That's still a connected period. Yeah. But even if you look at it like this, still going to get the same answers. Same 2 answers you're focusing on. What I really don't want you to do, though, is look at something like this. While technically correct because you have a whole, a half, and a half, now you're breaking things up kind of funny. Okay, so we'll just stick with that. All right, so the homework, it's on 352. It's 2, 3, 6, 7 to 10, and 13. 15, 20, 28. 29 to 31, 34, 45 to 48. A lot of it is graphing, so if there's nothing to write down, you can just put it on calculator, or if they do ask for a complete graph, just write your window. Okay, and we'll take a look at that tomorrow.